Hello everyone, welcome to lecture 5. So, the plan for this lecture is as follows. We will see a candidate for perfectly secure encryption, which we call as one-time pad, and we will see the limitations that are imposed by any perfectly secure encryption scheme. So, the one-time pad encryption process, which is also called as Vernam cipher, is very simple. Here the plain text space, the key space and the ciphertext space are all L bit strings, where L is some system parameter which is publicly known to the sender, to the receiver and to anyone who is using this system. The key generation algorithm is going to output a uniformly random key. So, since the key space is the set L bit strings, the key generation algorithm is going to output a uniformly random L bit key. The encryption algorithm is as follows. So, it takes the plain text, which is going to be an L bit string, and the key k generated by the key generation algorithm, which is also an L bit string, and the ciphertext is an L bit string, where the ciphertext is nothing but the XOR of the plain text characters and the key characters bit by bit. And as you can see that this is a deterministic algorithm, there is no internal randomness as part of this encryption algorithm. That means, if you encrypt the same message M using the same key k, you are going to get the same ciphertext. The decryption algorithm is just a reverse operation of the encryption algorithm, in the sense it takes the ciphertext, which is going to be an L bit string, and the key k, which is also going to be an L bit string, and to recover the message, the decryption algorithm just performs the XOR of the ciphertext with the key k bit by bit. So, just to recall what exactly is an XOR operation. So, the XOR operation operates with on 2 bits at a time, and the output is defined as follows. If both the bits are same, then the output is going to be 0, whereas if the bits are different, then the output is going to be 1. That is what is the XOR operation, right. So, in some sense you can imagine that this encryption algorithm does the masking of the message with the key, right. So, the XOR operation has the effect of masking the message bit by bit with the bits of the key, whereas the decryption operation, you can imagine it has the reverse operation of masking, namely unmasking the effect of key from the ciphertext bit by bit by bit. So, the important thing here is that since the XOR operation is kind of reversible here, you can mask the message using the key by performing the XOR operation, and to get the effect of unmasking, you just have to XOR the key from the ciphertext to get back your message. So, now let us prove that this Vernam cipher or one-time pad is indeed perfectly secure, and we can prove its perfect security as per any of the 3 definitions that we saw in the last lecture. So, I am going to prove that Vernam cipher is indeed perfectly secure over the message space of L bit strings, and for this I am going to use the first alternate definition of perfect secrecy that we discussed in the last lecture. Namely, I am going to prove that the distribution of the ciphertext is independent of the underlying plain text in any instance of Vernam cipher. For this, we consider an arbitrary probability distribution over the plain text space and an arbitrary pair of messages M0, M1 belonging to the plain text space as per that probability distribution, which has a non-zero probability of occurrence. And we also pick an arbitrary ciphertext which has a non-zero probability of occurrence. Now, what I am going to prove is that for any M0, M1 that we have picked here arbitrarily, and for any ciphertext C which we have picked arbitrarily here, the probability that M0 is encrypted in C and the probability that M1 is encrypted in C are same, which will prove that our Vernam cipher is perfectly secure. So, now let us first try to compute the conditional probability that if your plain text is M0, what is the probability that the Vernam cipher is going to produce the ciphertext to be little c, right. So, the probability that plain text M0 is going to produce the ciphertext little c is the same as the probability that the key which is used for encryption is this string, namely the key is XOR of M0 and little c. And what is the probability that the key which is obtained by running the key generation algorithm is indeed the XOR of M0 and little c? Well, it is 1 over 2 power L, because as per the syntax of our key generation algorithm, the key generation algorithm is going to output a uniformly random key. So, the probability that that uniformly random key which is obtained by key generation algorithm indeed satisfies the value XOR of M0 and little c is 1 over 2 power L. In the same way, the probability that the message M1 is encrypted in the ciphertext little c is the same as the value of key which is used for encryption is the XOR of M1 and little c. And again, since my key generation algorithm is going to output uniform random keys, the probability that my key is the XOR of M1 and little c is 1 over 2 power n. So, since both these two probabilities are equal, after seeing a ciphertext which is going to be an L-bit string, adversary cannot pinpoint whether it is an encryption of M0 or whether it is an encryption of M1, and hence the adversary will be completely clueless, and that is why this encryption satisfies the definition of perfect secrecy. So, we now have a candidate encryption scheme which is perfectly secure. So, now you might be wondering that if we have a candidate scheme which is perfectly secure, why can't we afford to use it in practice? So, now let us see some of the limitations which are imposed by the one-time pad scheme. The first limitation which is imposed here is that key should be as large as the plain text, because the size of the key is L as little l as well as the size of the plain text is also little l, right. This means that if you want to say encrypt 1 GB file, that means if the sender wants to encrypt a 1 GB file, then it has to agree upon a key which is also of size 1 GB, right, which seems very impractical, because in practice we aim to go for encryption process where we can use a very little size key to encrypt long messages. So, that is the first restriction which is imposed by Vernam cipher. The second limitation which is imposed here is that you cannot reuse the same key for encrypting more than one message. That means each instance of the encryption needs a fresh key. I stress here that when I say here that you cannot reuse the key, I do not mean that you cannot reuse the key in the next instance. What I mean here is that in each instance you have to again run an independent instance or a fresh instance of key generation algorithm. It is fine if the key that you are going to obtain in the next invocation of key generation algorithm is the same which you have obtained in the previous invocation. What is important here is that both these invocations of the key generation are going to output independent outputs. So, from the viewpoint of an adversary or an attacker who is intercepting ciphertext, he will not be knowing that the keys which have been used, whether they are same, whether they are different. From the viewpoint of the attacker, they are independent keys. So, the second restriction which is imposed here is you cannot retain the same key and keep on encrypting multiple messages using the same key. For instance, imagine a scenario where the sender is going to use or retaining the same key k for encrypting two different messages M0 and M1 in sequence. That means it has used the key k for encrypting first the message M0, communicated the ciphertext, and suppose it is again retaining the same value of key instead of again running the key generation algorithm, and it reuses the same key k for encrypting a next message M1, and again the ciphertext is communicated over the channel. And suppose adversary is aware of this fact that the same key has been retained and used by the sender to encrypt two messages M0 and M1. So, now what an attacker can do is the following. Since it has intercepted the ciphertext C0 as well as it has intercepted the ciphertext C1, and it knows the relationship between the messages M0k, M1k and C0 C1, namely it knows that C0 is the XOR of M0 and k, and it knows that C1 is the XOR of M1 and k. If it performs the XOR of C0 and C1, the effect of k is going to vanish, right, because that is what is the property of the XOR operation, because k will be XORed with k itself, which will give you 0, and as a result by performing the XOR of C0 and C1, the adversary is going to obtain the XOR of M0 and M1. So, now you might be wondering how much information is actually revealed by learning the XOR of M0 and M1, and it turns out it is a significant amount of information. And that means we cannot claim the perfect secrecy for this kind of encryption process, where the same key is now retained for encrypting multiple messages. So, here is what Turing Award winner, legendary computer scientist Michael Rabin has to say about one-time pad. He says that you should never reuse a one-time pad. It is like a toilet paper, because if you reuse it, things can get messy, right. So, you should never reuse the key. For each instance of the one-time pad Vernam cipher, you need to run a key generation algorithm and obtain a fresh key for encrypting your next messages. So, these are the two restrictions imposed by Vernam cipher. Now, a natural question is whether these two restrictions are only with respect to one time pad or one name cipher, or are these two restrictions inherent to any perfectly secure cipher. What we are now going to prove is that these two restrictions are inherent for any perfectly secure cipher. Namely, in any perfectly secure cipher, key should be as large as the plain text, and we will also prove that any perfectly secure cipher, each instance of the encryption needs a fresh key. So, let us first prove the first limitation here. So, the theorem here is, imagine you are given a perfectly secure cipher. It need not be one time pad, it could be any perfectly secure cipher. The theorem says that if the scheme is perfectly secure, then the key space has to be as large as the message space, right. So, here is the proof. The proof is going to be by contradiction. So, on contrary, imagine that even though my scheme is perfectly secure, my key space is less than my message space. That means, the number of candidate keys is less than the number of candidate plain text. And for demonstration, here is an example. I am assuming that my candidate plain text space consists of 3 plain text and my candidate key space consists of 2 possible keys. So, now you consider the uniform probability distribution over the message space. That means, you consider a scenario where sender could have encrypted any of these 3 possible messages with equal probability, and you consider a ciphertext with whose probability of occurrence is non-zero, right. So, now let me define the set M of C, which is the set of all valid decryptions of the ciphertext C. Namely, M of C consists of all plain text M from the plain text space, which I can obtain by decrypting the ciphertext C under different candidate keys from the key space, right. So, again in this particular example, if I try to decrypt the ciphertext C, I have 2 possible keys. On decrypting ciphertext C by K1, I will obtain 1 message, and on decrypting cipher C by the second key K2, I will obtain 2 message. That means, what I can say is that the cardinality of this set M of C is upper bounded by the cardinality of the key space, because that is the maximum number of distinct decryptions you can obtain by decrypting the ciphertext C here. And since, as per my assumption, the key space cardinality is less than the message space cardinality, what I obtain here is that the cardinality of M of C is strictly less than the cardinality of key space, which is less than the cardinality of message. What it means here is that there exists at least one message from the message space, plain text space, which can never lead to the ciphertext C. That means, on decrypting the ciphertext, I will never obtain back that plain text. Again, in this specific example, you can see that the decryption of C can never give you back M3. And that is a violation of the perfect secrecy condition, because the perfect secrecy condition says that if you have a uniform probability distribution over the plain text space, then for every ciphertext C which occurs with non-zero probability, it should be an potential encryption of all candidate messages with equal probabilities. Or in other sense, if I see the original definitions of perfect secrecy, what we have arrived here is the fact that we have at least one message is little m, where the probability of occurrence of the little m is non-zero, but the conditional probability that little m is encrypted in the ciphertext little c is 0. That means, these two probabilities are not same, and hence that is a violation of perfect secrecy, right. So, that means we have proved that in any perfectly secure encryption scheme, the key space has to be as large as the message space. Now, what is the implication of this theorem? Imagine your key space is a set of all possible strings of length x. That means, my encryption process supports encryptions of x bit strings. That means, the key space is cardinality is nothing but 2 power x, and in the same way, imagine my encryption process supports plain text space of y bit strings. That means, the plain text have to be y bit strings, and as a result, the cardinality of my message space is 2 to the power y. Now, as per this theorem, if my scheme is perfectly secure, I need the cardinality of the key space to be at least as large as the cardinality of the message space. That means, 2 to the power x should be greater than or equal to 2 to the power y, and as an implication of this, I get the fact that x should be greater than or equal to y. That means, the length of the key should be as large as the plain text. So, that is the first limitation of any perfectly secure cipher, namely the key should be as large as the plain text. Now, let us prove the second limitation of any perfectly secure cipher, and I will not be proving it rigorously and formally. I will just give you a very high level detail of the proof here. So, the theorem states that imagine you are given a perfectly secure cipher over the plain text space M and the key space K, then each instance of the encryption process of this cipher should require an independent key to be generated by the key generation algorithm. That means, you cannot retain the same key for encrypting more than one message here. So, now let us again try to prove this using contradiction. So, imagine a scenario where sender retains the same key K for encrypting two messages M1 and M2 in sequence, right. So, it has encrypted message M1, produced the ciphertext C1, communicated over the channel, and then it has used the same key K for encrypting a second message in the sequence, and again the ciphertext is communicated over the channel. And adversary has intercepted both the ciphertext, and adversary is aware of the fact that the same unknown key K has been retained and used to encrypt both the messages M1 as well as M2. What we are going to prove is that if something of this sort happen, then you can never achieve perfect secrecy, right. So, imagine two different sequences of plain text. The first sequence is when the first message is M1 and the second message is also M1, and in the second sequence M dash, the sequences of messages are M1 and M2, where M1 and M2 are different. And imagine that adversary has intercepted a ciphertext consisting of two sequences of ciphertext, where the first ciphertext is C1 and the second ciphertext is C2, right. So, as per the requirement of perfect secrecy, if the adversary has obtained the sequence of ciphertext being C1 and C2, and if adversary has a prior information that the two sequences of messages which could have been encrypted in C1 C2 could be either M1 comma M1 or M1 comma M2, then the requirement of perfect secrecy is that with equal probability the ciphertext sequence C1 comma C2 should be an encryption of M1 comma M1, as well as it should be a potential encryption of M1 comma M2, right. That means, if I consider the left hand side probability here, then I have introduced here two random variables C1 and C2 in boldface, which denotes the value of the first ciphertext sequence and the second ciphertext sequence, and in the same way I have introduced two random variables boldface M1 and boldface M2 to denote the candidate first plain text and the candidate second plain text. So, my claim here is that the probability that your left hand side probability and your right hand side probability can never be same, which is a violation of perfect secrecy. Pictorially, the requirement of perfect secrecy should be that it does not matter whether the first message sequence M1 comma M1 is encrypted, or whether the second sequence of message M1 comma M2 is encrypted using the key. As per your encryption process, with equal probability it should lead you to the ciphertext sequence C1 comma C2, if at all your encryption process is perfectly secure. But if that is the case, that means imagine a scenario where indeed the message sequence M1 comma M1 and the message sequence M1 comma M2 both leads to an encryption ciphertext sequence C1 comma C2 with equal probability under the same key K, then it means a decryption error, because that means that if you decrypt a ciphertext C2 using the key K, then it should be leading you back to the plain text M1, as well as it should lead you back to the plain text M2, which means that there is a correctness error in your encryption process. That means there is a decryption error in your encryption process, which is a violation of the fact that your encryption process is secure, because one of the requirements of any secure cipher is the correctness requirement, which demands that your decryption should be unambiguous. But if we are in a scenario like this, where both the message sequence M1 and the message sequence M1 M2 leads to the same ciphertext sequence C1 comma C2, that means if I just decrypt the ciphertext sequence C2, it could lead me back to M1 as well as it could lead me back to M2. That means there is an ambiguity in the decryption of my original encryption process itself, which is a contradiction. This proves informally my theorem that each instance of the encryption process should run a fresh instance of the key generation algorithm, right. So, that brings me to an end of this lecture. Just to summarize, in this lecture we have discussed and candidate perfectly secure encryption process, namely one-time pad or Vernam cipher, and we proved its perfect secrecy. We also saw the two restrictions imposed by one-time pad, and we argued that these two restrictions, namely the key size being as large as the message and fresh key for each instance of the encryption, are inherent to any perfectly secure encryption process. I hope you enjoyed this lecture. Thank you.